So last time of our two numerical lectures, we did finite difference, which is really good for one-dimensional problems. Set up the Hamiltonian, MATLAB does everything from there, right? It's really unbelievably easy. Split operator is a little bit difficult. It's one thing that's very good about this is that you can extend it to 3 dimensions quite easily. Whenever you see the code, when you see the operators, the potential and kinetic energy operators, that's the split operator of the split operator method. And you see it's like e to the I x, right? All you would do is multiply that times e to the I y times e to the I z. And that's how you make it 3-dimensional. So in other words, it's incredibly trivial. All right, and of course what we're doing in the Schrodinger frame is we are going to time evolve a wave function. Let me put this as delta t. We're going to time evolve a wave function. Well, yeah, just to state. You can start with anything you want. In fact, you really don't want to start with an eigenstate of the Hamiltonian because, as we talked about, nothing really happens. Regardless, so this is the idea, and again, you're seeing the Schrodinger picture where I'm not time evolving operators, I'm time evolving the wave function. Of course, the Hamiltonian is this, and where you're going to get created is, of course, is the potential. And it's one-dimensional. So again, I threw some ideas of potential energy surfaces where you have to figure out how to plug that into the computer. Again, it's not hard, and but it makes it yours. It makes it more interesting. And of course, momentum is. Now, one thing I want to point out. I want to tell you this word that you hear. You're going to hear this term. It's called non-locality. And what that means is it's applied to momentum. You're going to hear about non-local operators and how hard they are to deal with. What this means is it means momentum. Momentum is a non-local operator. Now the idea is, if you recall finite difference, I had to know the point. To get the slope at a point, I have to know the point ahead of it or the point behind it. I have to know its local environment. So it's not enough to know what the wave function is at a point. You have to know the wave function at other surrounding points. Hence non-local. So people like to use those kind of, again, highfalutin types of sounding words, but they're very easy to understand if people chose to make them understandable, but they don't. Okay, so I'm just writing, so there's our time evolution operator, and again, we're applying that to a state. Okay, so here's what we're going to do. All right, so now I've got two terms, e to the a plus b. What's e to the a plus b? Yeah. Okay. Here, let me write that down. Here, and I'll do momentum first. Sorry, it looks like I got a. Yeah. Sorry, slight problem with my notes. Threw me off there. Yeah, there we go. Okay, so I'm just doing what you just said. Okay, right? Nothing wrong here? Yeah, okay. Now, you know that, we're of course going to start out with the wave function. Well, let's say that we know what it is as a function of position. So I'm going to say that I'm going to simulate a 0 to 1 nanometer I'll center this as a Gaussian shape. There'll be a bell curve that, oh, it's a harmonic oscillator, right? So I'm going to center this in the 1 to 1 nanometer, and the potential will be a parabola centered at half a nanometer, right? So in other words, it's just unbelievably simple. Okay, now potential energy wave function. You know the way that works is, by the way, I'll exaggerate this. What you're doing, if you have this, and you know you have e to the IV, e to the I potential, but let's not worry about that. Potential times wave function means you're just at every point, you're just multiplying the results. You see what I mean? It's kind of funky, but what you do is you multiply that by that, and then that goes here. Now that's here. And then you multiply that by that, that goes here. You multiply that by that, that goes here. Multiply those two together. Anyway, you see what I mean? You're just multiplying them together across x. It's really simple. You know, you can look at this sometimes and think, well, wait a minute, wait, what does this really mean? This is what it means. It's the most brainless thing possible, right? Okay, now just do e to the minus potential, right? Just do this, and it's still just a number, right? So it's not hard at all. Okay, now, but what are you going to do about this? Because that's not local. What are you going to do? Looks like you got a bit of a problem, don't you? Okay, now, you've actually seen the resolution to this problem several times, including an exam. What should I do about this operator? Given that you've seen the answer many, many times.
Psi x to psi p.
Fourier transform. Fourier transform the wave function. So what you're going to do is, again, you've seen how unbelievably trivial. You've seen how unbelievably trivial look, you know, when you're in X space, right? So you're going to do this operation just like I said. Again, as brainless and simple as imaginable, and MATLAB does it all for you. If you look at my code, when I defined the operator, I said that the V operator is exp minus I del t potential, and h bar, of course, we're going to be in atomic units, that's 1, so it doesn't exist. So, simple. You Fourier transform, after you do that multiplication, you Fourier transform it, and then you just do the same thing again. Now, the trick here is to know what the x is. So you notice how, well, I'll tell you how to do this in a minute, but anyway, that's the idea. And then you're going to basically inverse Fourier transform back, and you're going to, and now you've basically done a loop. And so you go back here, you go delta t, you go delta, anyway, over and over and over and over and over again. Okay, now there's one giant problem with this. So, I mean, this lecture would be done if this was actually true, but there's a problem. Okay, who says I did it in this order? Is there ever a problem with the order of operations, of operators? When is operator A, operator B not equal to operator B, operator A? Because remember, each one operator is still an operator. This is just a function of the P operator, this is a function of the potential operator, which is basically the X operator. Okay, so when would operator A, operator B not equal to operator B, operator A? When does that happen? Over there?
And they don't come
Yes, they don't commute. What do momentum and position commute? No. Who says I put it in this order, right? It was arbitrary because I wrote it this way. I could have easily done it the other way. And then guess what? You're going to get a different result. Well, that's pretty screwed up, isn't it? Because time evolved in only one way. Yet I have two possible outcomes. So something's screwed up. So it turns out it's a mathematical fact because, again, there's nothing magic about quantum mechanics. So it's all just, once you set up the Schrodinger equation, you can just look up mathematical principles and know how things work. So A is obviously going to be like momentum, and B is going to be position. So it's kind of obvious what I'm trying to do here, right? So here I'm basically saying here's the propagator. This is called a propagator, by the way. The time evolution operator, you'll often hear it called a propagator. Okay. What I did was this. I did this, and of course, they are not equal. And this was a known mathematics long before Schrodinger this or that. So there you go. Okay, so what it is let's see here. The way you do this is called again, I'm sure that these are just mathematicians. Baker, Campbell, Hausdorff. Okay, this is their formula. Okay, so the way this works is e to the, oh my God, lambda a, oh no, wait, sorry. So you kind of reverse engineer it. So remember I said you actually don't want this, right? But here's how the formula works. Okay. So this is what we want to be true, right? We want these to be true. I just reversed them. But it turns out that's really not the case. It turns out that then you've got commutators. And it kind of makes sense because there's a commutation error. So to some degree, maybe you can think of this as like you're removing the commutation error with commutators. And then you've got these nested commutators. And again, so this would be like, if that's position and that's momentum squared, then this is momentum. So that's like position momentum, which is IH bar. So you can figure this out. And it goes on and on and on. So here you notice that I then permute A and B. And it goes on forever, by the way. Okay. So, the point of this here, if anyone cares, you can look it up. If anyone cares, that we're basically gonna stop here. So again, here's my Hamiltonian, and I am gonna still do this. I'm still gonna do this, but you should know it's not right. Okay, it's not right to the order of lambda. Right, so these terms have a bunch of lambdas in them. Well, these do too. So to minimize, all right, so to say that these two are equal is obviously the error. The error is proportional to lambda, which is proportional to delta t, your time step of the simulation. Ergo, how do you minimize? Oh, sorry. Actually, what I meant to state was, I have to. Oh, I'm a little confused about this, but I have to double check this formula. These terms are proportional to lambda squared, and these terms are proportional to lambda. So I'm a little bit lost about this. So I can kind of see lambda squared here because you can see a nested, you have two commutators with both of lambda, so I can kind of see lambda squared here. I'm a little confused about, oh, wait, of course there's lambda squared, right? This times that, right? Lambda squared, lambdas get multiplied. Okay, I see it now. Okay, so these have lambda squared. So your error is proportional to lambda squared, which is proportional to delta t squared. So how do you minimize the error? Yeah, make it small. Make your time step really small, like 2 to the minus 17 seconds small, right? Remember a natural time unit? Okay. So anyway, now this is why there's an error. And I just wanted to point that out. This is why you want delta t small. Now there's another way to look at this. There's another approach. So this was just to make it clear to you that you can't actually do this. But now the way to really get this to work is called, it's actually related, Schrodinger product rule. And the way that works is, again, here is our Hamiltonian. We're going to have okay. So there you go. So there you go. Not much else I can say. Okay, now what we're going to do. So, of course, these are really, in some way, they have to be the same thing. They're related. So if we're going to do this at m equals 2, what you're going to do is, and you have to look out for this. This is called the symmetrized product. You don't have to use the symmetrized version of this. And let me show you what I mean. Like, what do you mean symmetrized? Okay, so if we're going to truncate at m equals 2, we square it. But notice that I flipped. So I got a, b, b, a. That means that's symmetrized. You don't have to do it this way. You go a, b, a, b. You could do that. But apparently it's like it doesn't really matter. And the reason that you might want to do that is this. You can combine these terms now. So you can do that. Okay, so that now brings me to the algorithm. So what I was doing there, sorry, I shouldn't erase that. What I was doing there was going to give you a rough idea of what we're trying to do here. But now that I've done all this, now I can actually write it out for real. And again, you just got to understand that I'm making approximations. And based on that, that first deal I wrote, the Baker, Campbell, blah, 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 you understand that it's an error depending on the time step. Smaller time step's good. So here's how it's going to go. Okay, so here's t squared. So all these I delta t's are the same. Again, we're going to be h bar. H bar isn't really there. Potential energy, again, you're going to make that up yourself. There we go. All right, so there you go. That's how you do it. Okay, so what we're going to do here is we start with this. Notice this position. Fourier transform. Do this. Fourier inverse Fourier transform. Fourier transform. And then actually do this again. Fourier inverse Fourier transform. Inverse Fourier transform. Fourier transform. Back anyway. It's a loop. You'll see it in the algorithm. Relatively straightforward. Okay, so you do this over and over and over again. And again, maybe it's a little cross-eyed about how you jump from here to here, but you learn by doing. The program you can see, and then you'll modify it, will make it really clear. Okay, so that is how you time evolve numerically in the Schrodinger frame. Next bits. Here's some really cool things you can do. You can calculate the spectrum of energies. Of course, let's assume that you're using a quantized system. So you'll see all the bound energy levels. You can calculate, now remember, we're at the end. When I say psi, I mean the eigenstates of the Hamiltonian. You can calculate the eigenstates of the Hamiltonian. So you can do both these things. So in other words, you basically get everything you could ever want, energies and eigenstates, while making movies of this thing bouncing around over time, which is ultra cool. Trust me, when you cut and paste my program and watch it go, you're going to love it. And then I hope if you're the kind of person who took this class, hopefully on your own, you'll get fascinated by changing it on your own and watching it do new things, including go haywire. Let me point out that if you use a time step that's too big, potential energies that are crazy, wave functions that are nuts, the simulation will go out of control. And you are going to do that, by the way. You'll know when it happens. It's like hard not to notice. So just heads up on that. All right, anyway, how do you do these? Okay, for this one, you're going to actually have to run the simulation twice. The first time calculates the energies, and you need that to calculate the wave functions. That's why you have to do this twice. It's also called a spectral method. If you ever hear that term, a spectral method, this is what you're doing. Okay, here's how you do it. I call it core in the program. Okay, correlation. That's what it means. I call it core. And you're going to Fourier transform core. Correlation is a signal. The signal is this. It's the overlap over time of this state with the initial state. Okay, so you only have one of these. You set it up yourself at the beginning. And again, I start with the bell curve slightly displaced from the center of the potential. And then this is resulting from the algorithm. If you do 1,000 steps, you'll have 1,000. The signal has 1,000 somethings. Okay, it's going to look like this. It should start at 1. It's going to start at 1 because this is that at the beginning. And it's going to go Now it's going to be real and imaginary. Right? So, I mean, you can see I've got imaginary numbers, so this might be and of course the imaginary would start at 0. And this is, again, using MATLAB terminology, real, IMAG imaginary. Okay, so just so you know. All right, what the heck is this? This is this. Let's think of, I'll go to a ket, but you know the dual correspondence to a bra. You know that everything can be cast into the form of a basis. And you know how a basis evolves in time basis of the Hamiltonian. Or, sorry, I'm using really bad terminology here, aren't I? I'm assuming that so I should be, so you know what I'm verb right now, I should have been using psi. Because I kept saying psi is for Hamiltonian, right? So notice sorry, I'm kind of mixing up my terminology. So this ket AN is an eigenstate of the Hamiltonian. It returns A to the E of energy, and the ket comes back. So that's just the eigenvalue equation. Okay. So any wave function, no matter how crazy it looks, because the cat drew it, instead of being a nice Gaussian, the cat drew it, over time it turns into something that looks like the other cat drew. It can go nuts on you. Doesn't matter. In the complete basis set of eigenstates, it can be represented. And evolving in time, I'm just using the time evolution operator. It's just I went ahead and operated on the Hamiltonian on the operator, and we know that's not minus I Hamiltonian, it's minus I eigenvalue, which is E energy. So there you go. Okay, what do you do with that? Now that you know that that's what that is, this correlation function, and I'm showing you what it looks like. When you cut and paste my program, try that. Try plotting the real and imaginary values of the core of COR, and you're going to see exactly what I just drew. Well, not exactly what I just drew. What I just drew looked crazy. Regardless, knowing that that's what the bra is, what you're going to see is this. Oops. NH bar is 1. Okay, so what it is, now remember e to the something times t. This is just cosine minus I sine, right? So it's just a bunch of curves. Wiggle, 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 wiggle. Real and imaginary. Oh, and that's how much any particular state of all the eigenstates contributes to whatever the hell it is your simulation is doing. Okay. So what you then do is at the end of the simulation, for various reasons that are kind of funky, I'm sorry, there's something about this that's slightly non-standard. You're going to do IFFT, the inverse Fourier transform. It's a weird reason. It's the, actually I kind of forgot. It's like, the propagator is like a forward transform. So to get the energy spectrum, you do a backward transform. It also has to do with positive versus negative energies. I'm assuming that you're going to do positive energies, right? So your potential energy begins at 0. So you're actually going to do IFFT of the correlation. And what that turns into is a sum of the weighing coefficients of the energy state, and your x-axis is energy, and you're going to see a spectrum there of basically a bunch of delta functions. That's not quite right. So what happens is, again, run that program and plot the inverse Fourier transform of the correlation function, and what you're going to get. Now again, MATLAB plots things according to data number, right? Data point 5, 6, 7, 8, 9. That's how MATLAB intrinsically works. What you're going to see is something like this. You're going to see something, now again, I've obviously not quite done that correctly. I made these curves a little smoother than the x-axis implies, okay? So sorry about that. But anyway, this is what you get. You get peaks that correspond to energies. Those are the energies of the states of the Hamiltonian. Remember, you want to see energies, you're getting the eigenvalues of the Hamiltonian operator. Now, heads up, due to some oddities about how all of this algorithm works, and I don't want to bog you down with details, it's a bunch of algebra. The energy, for every peak you see, the energy is peak minus 1 times 2 pi over okay, that's the formula. Again, I don't want to bog you down with details. Again, we kind of need to move off of this as quickly as possible. But okay, in this case, 3 times 2 pi over 1,000 time steps. Again, you can play with that. Delta t, let's say 1, right? And so then that gives you the energy. And the energy would be in Hartrees because you're using atomic units, right? You're not plugging in 2 to the minus 17. Okay, you could. I don't know what the energy would be. It would be energy, I just don't know what units. But if h bar is going to be 1, the mass of the electron is 1, time step is 2 to the minus 17, but we call it 1. Okay, so one thing you're going to notice in my program, I used the CO vibration as an example. So the mass is huge, right? Because CO, the reduced mass, in masses of electrons, it's, you know, it's like 10,000 or so. Anyway, it's a big number. So anyway, atomic units, we've covered this. Okay, so that's how that works. Now, last bit is how do you get the wave functions. You're going to calculate, once you have those energies, you can calculate the ground state versus excited state. I mean, any that show up in your spectrum. You can then calculate the wave functions, unnormalized wave functions, by rerunning the simulation from the beginning. You have to know those energies. Now, the way that works is you're going to do this integral. You're going to go from 0 till you're up here, steps, number of steps, technically times, so this is in time. So I'm just saying, you know, here's the thing. You'll have to see theory papers, and they're going to show something like this, right? Oh, look at this. Oh, this is crazy. This is a code for rerun the trajectory. That's actually what this means. I know it's an integral sign. I'm telling you what it really means. Rerun the trajectory. Okay, I've got this, which you have just figured out. I'm going to call it, no, I'll call it that. I'm going to give it a dash. Now, this is what you just figured out from having run one time. This is your trajectory from the calculation. Okay. Now again, the papers you see say this, but now you've got to actually interpret it. Remember, I know engineers, you know about stress and strain, but now how thick should the flange be, right? There's this disconnect there. How do you actually bridge that gap? This is the answer. What does it mean? Okay, 0 to the length of the trajectory means you're rerunning the trajectory. This, the energy was determined here. So the ground state energy, the number you plug in is, that's 4 minus 1, 3 times 2 times pi over number of steps delta t. That number goes in here. Again, we know what the time step is, h bar is 1. And you multiply this times the wave function at every step. Now, an integral is just a sum. It's just a sum of things multiplied. So, so what you do is, you know how you add things in a for loop? For I equals 1 to link the trajectory. The wave function is, which you'll set to like 0 at the beginning, is equal to the wave function plus this term. So it keeps building, building, building. This is how you add something. Okay, in the algorithm, that's how it works, and just check it out, you'll see it. Now, the reason it works the way it does is, let's now think about what is this guy expanded in the basis set eigenstates of the Hamiltonian. And so here's this factor there. Now, the energy of the eigenstates goes as e to the minus I energy. So you see that that's subtracted. Let me go back and use my terminology. Let me go back here. So again, I kind of flunked my use of symbols. I'm not using consistent symbols, so sorry about that. But okay. What I've done is I've substituted, and again, you know this. I've already covered this. T and H bar. Sum of all states. Sorry about that. I'll get a new kid here for a second. Okay, so again, the wave function can be decomposed into the basis of eigenstates of the Hamiltonian that evolve as e to the I energy, e to the minus I energy. So when I multiply that e to the plus I energy, you get this. Now, if you plug in the ground state energy here, and that's the ground state energy there, this is 0, and this is going to build in the circle. Kind of see what I mean here? If this is the first excited state, then only the first excited state builds, because everything else gets wiped out, because it's basically being multiplied by itself plus a sine wave, and the sine wave deconstructs to 0. Kind of see what I mean? So I know I'm kind of rushing here, and I hope this is, if it's not clear, again, nothing is going to help you like a program. In fact, let me do that. Let me just do this parting shot. Let me show you what the program will look like. So, and again, this is in the code. Okay, so while you are in the program, you're going to have a for loop. You're going to start at time step 1, and let's say you do 10,000. You usually do a lot. You're going to do many steps. You don't do this like 10 times or 100 or 1,000. You want to do at least 10,000. Okay, so the first eigenstate, which has been initialized already to 0, builds up this way. And of course, and this is the language I use in that. This is the energy I use in the language I use in the program that I sent you. Now I don't have H bar. I don't have H bar in the program because it's just 1. I am including it here so that you don't get completely confused about what is happening. Okay, so again, the ground state is equal to the ground state plus this right here, and the energy having been determined from the previous run. Here's your, I call it DT, sorry, I call it DT in the program. T is T, H bar doesn't exist in the program. And again, psi of T is actually somewhere in here. So you're doing your loop over time. Your time evolving psi of T here, I should have left a little space here. Again, the algorithm I've already covered, and you can see it, and then this is what comes after. But notice, you see why you have to write it twice. you don't necessarily know the energies until you run it the first time to get the correlation function. You run it the first time to calculate the correlation function, you get the energies, you run it a second time, and then you cut and paste this code into it. And then plot I1 and I2, and it's quite clear that it works. And just you get the unnormalized wave functions. So, yeah, with that, that is that when it comes to the split operator. And I'm going to just largely leave it. To your exploration of the program, because you kind of have to on the homework. And again, I know I'm being a little too fast here, but I just needed to finish this. So I just want to get on the next subject just for the next, clock's a little slow, I've got 4 minutes. Nothing beats learning by doing, right? That's why I am such a big fan of the computer, is that I find all of this way too abstract. But when you actually get a computer to calculate all this stuff, then you really have to understand it. You really understand what's going on. And again, I've tried to facilitate that as much as possible by giving you code. Hopefully, it's not also a complete shortcut at the same time. Okay, with that, I know this is ultra fast. We're going to spend, I just want to introduce this, we're going to spend Monday and then virtually Wednesday on perturbation theory. Perturbation theory. I don't have a question on the homework on this, which was kind of a mistake on my part, whatever. And then the last week is angular momentum, which is actually, I mean, at first it's kind of painful, but then you learn some things that make it really cool. You learn how to do term symbols of metals. So of atom. Actually, I'm going to have you do carbon and nitrogen on the homework, but it's really useful for metals. And metals are catalysts, right? Okay, now, so I'm just going to introduce the core concept here. And it starts out as a mathematical, as like, the way it was presented to me when I was your age, is that if you know this, if you have a Hamiltonian that's composed of something simple and something a bit more complicated, just assume that it's a function of position. It always is. It could be true that you know the eigenstates and energies of this part. If this wasn't here, say that this is like light. So this is the perturbation due to light. I don't know. Your instrument. This is your chemical species. Your instrument comes along, is going to screw with it. But before it was there, you knew what you knew everything you needed to know. Okay, cool. The idea of perturbation theory is that along comes a spider, and it ruins your ability to do this. Now, see, if you know this, then you know everything, right? So this is your complete Hamiltonian, and if you can operate on that sucker times the wave functions, which you also know, and get the energies, then you're set. You know, this is what we've been talking about the whole time. Now, the way this was introduced was what happens when actually you don't know this. What happens when you don't know this? You just literally don't know what it is. You know this part. What do you do? In other words, perturbation theory is often presented as what happens when you have a mathematical conundrum, when you are not smart enough to solve the Diffie that is the whole problem. Instead, you solve a part of the problem you can solve, and then you're going to make an approximation to this. So perturbation theory is an approximation to this equation. I know this, I can't know this, so I'm going to do this perturbation theory and I'm going to get close. That's the idea. Okay, so that's stupid. The reason it's stupid is because I've got computers in discrete Fourier transforms and finite difference method that I can actually solve anything if I just use the numerical approach. There's nothing I can't solve with computers now. I don't need to do this. You know, this perturbation theory, it's actually kind of dumb. It was just like presented as like a solution to a bad math problem for chemists. What it really does, so why am I even teaching it? Because it teaches you to think about how your molecules react to your instrumental probing. So you want to understand this, but you're always probing it with that, and it changes things. So what this does is it allows you to think about this, understand what your machine does to change things, but again, it allows you to think more about this way. So that's actually incredibly valuable. Last bit I will go over is the idea. The idea is to change the Hamiltonian. Notice I haven't really done anything, but I'm going to multiply the potential part, the part that's actually kind of messing things up and doesn't give me a solution. I'm going to multiply it by lambda, and lambda is going to go from 0 to 1 as I solve it. Anyway, so with that, I'm out of time. So Monday and Wednesday, we're going to talk about, again, this method of approximating solutions to a Hamiltonian that we can't solve. But again, my point to you is not to really look at it that way. Look at this as you want to understand your molecule, understand that you're perturbing it when you measure it, and you need to understand what the nature is of that perturbation. Because remember, every time you study a molecule, you are actually changing it slightly. And that may mean that your observations are actually kind of screwing up your understanding of what that molecule is actually like. You always have to keep that in mind when you're doing experiments. You're